Ready to draw this? My husband says it looks complicated, but let's just take it one step at a time. It's not that bad. In the video today, we are going to be studying protein folding. Proteins are made of only 5 different atoms: carbon, hydrogen, oxygen, nitrogen, and sulfur. Keep in mind that our entire body is comprised of 6 different atoms: CHONPS, the P being phosphorus. However, there is no phosphorus in proteins. There are 4 levels of protein folding. Primary, and we denote primary with a 1 with a degree symbol there. Primary, secondary, tertiary, and quaternary. I'm actually going to be starting off describing the quaternary configuration because I find with complicated lessons, it's helpful to actually start with the most complicated version, believe it or not, and then move our way backwards. Perhaps you have seen proteins drawn in their sort of molecular configuration before. It always looks like a lot of different squiggles. So what I'm going to do for you now is I'm going to draw for you a hypothetical protein that, again, appears to be a lot of squiggles. This is a typical look of a quaternary folding of a protein. And it just sort of looks like random, just squiggles kind of overlapping each other. Oftentimes these are portrayed in different colors. So now what we're going to do is we're going to take some of the mystery out of that, and we're going to go backwards to the, we're going to work our way backwards through the tertiary folding of a protein. And with a tertiary folding of a protein, we're just kind of looking a little bit closer in at some of the shapes that we see inside of there, and more carefully drawing. We're sort of unfolding this a little bit just to get a closer look at some of those squiggles. And in this, we're then able to choose a few things that are recognizable: an alpha helix and a beta sheet. We'll come back to the tertiary folding. But for now, what we're going to do is take a closer look at the alpha helix. An alpha helix, be careful how you draw this. You want to draw it sort of like a ribbon, and it's kind of hard to portray a ribbon three-dimensionally. Hopefully I'm doing a decent job of it here. It is an alpha helix, so you have to think about the way that this is sort of twisting around itself like an old-fashioned telephone cord, if you have any idea what that actually looks like, which I don't know if you do. Hey, Grayson, do you know what an old-fashioned telephone cord looks like?
Yes, it's a curly thing.
Okay, so there's hope. My 9-year-old knows what it is. So there it is, an alpha helix, at least a small chunk of one. And the next thing I'm going to draw is the beta sheet. I'm definitely not very good at drawing the beta sheets, but just to give you an idea, sort of as you see, it's sort of like lines that instead of curling around themselves, they're fitted into a kind of a horizontal sheet next to each other. The alpha helix and the beta sheets are really the secondary configurations. There's a few other things that you'll see in the secondary configuration, but these are the types of shapes that you'll see very regularly. Now what we're going to do is we're going to go ahead and use a different color. I'm using blue in this case, to draw lines that show how these things actually form this shape. So I'm using dotted lines to indicate that it's a bond, that it's an attraction, kind of a magnetic attraction between these structures, in the midst of these structures. And these are hydrogen bonds. Now, a hydrogen bond is a rather weak bond. It's very easily breakable, which is why proteins can denature so easily. It's one of the most important bonds that they have, and it's a really weak bond. But it's a bond between a partially negative oxygen atom and a partially positive hydrogen atom. I'm annoyed that I did not actually use a dotted line between these two. But anyway, picture a dotted line. Draw a dotted line instead of a solid line between the two. Generally speaking, without getting into the weeds of how valences work and how electrons spin around the center of atoms and so on, generally speaking, when an oxygen is attached to anything, negatively charged electrons tend to kind of migrate in the direction of the oxygen, therefore giving it a partially negative charge. When hydrogen is bonded to just about anything, the electrons tend to kind of migrate away from the central part, the actual nucleus of the hydrogen, and therefore giving that hydrogen atom a partially positive charge, and therefore we say partial positivity and partial negativity. Sometimes that's enough for this partially positive hydrogen and this partially negative oxygen to sort of be attracted to each other. They are not technically attached to each other like with a covalent bond, for example. So there shouldn't be a line there. It should be a dotted line. But at the same time, they do have an attraction that is profound enough to cause this secondary configurations, either an alpha helix or a beta sheet. We're now going to be moving to the primary configuration for protein folding, and in this way we have to begin simply by drawing an amino acid. So an amino acid has an extremely stereotyped structure. There is a central carbon, there is an amine group on one end, which is NH2, shown here. And there's a carboxyl group on the other end, which is a C double bond O, single bond OH. I'm going to go ahead and draw two of them for good measure. There's the amine end, the central carbon, and the carboxyl end. Without getting into organic chemistry too deep, we will say that carbon always has 4 bonds. As you can see, the central carbon has an attachment to an N, an H, and a C, and then it also has an attachment to an R group. The R group is variable, and we will be discussing it later. Let's go ahead and label the amino end, amine end, A-M-I-N-E, and the carboxyl end. The carboxyl end is also called the acid end or carboxylic acid there on the end there. So that's how an amino acid gets its name. It has an amino end and it has an acid end. Next, we're going to go ahead and bond these two amino acids together. And in order to do so, we have to remove, exactly as you see, we have to remove a molecule of water. One H from the amine end of the one, and an OH group from the carboxyl end of the other. Together, these form a molecule of water. And in this way, especially in the presence of a particular structure in the cell called tRNA, transfer RNA, we're able to take these two monomers, single units of amino acids, and attach them to each other. The carboxyl end, now missing an OH group, has now attached to the amine end of the next amino acid. This is how they're always attached to each other. And I went ahead and made sure to still leave those R groups or those side chains intact because they actually don't have anything to do with this bond. This bond is called a peptide bond, and it's always between the carboxyl end of the one and the amine end of the next one. When we take single things and put them together, we have to remove a molecule of water, and it's called a dehydration synthesis. Dehydration in that name, of course, means removing a molecule of water, and synthesis means putting things together. Once you remove this molecule of water, the amino acids that are left behind are slightly less than they were before because they're missing, functional groups. And so now technically each of the amino acids would no longer be called an amino acid, but rather an amino acid residue, basically a portion of what it used to be. Now I'm going to tie together something that I said earlier, and I'm going to assign that oxygen there a partial negative charge. And I'm going to assign any given hydrogen a partially positive charge. And now we're going to be moving on to the secondary configuration, but when we describe the secondary configuration, what you must understand is that these amino acids that we're attaching to each other Up above, I've only shown 2 amino acids attached to each other, but of course there can be multiple. You can do one after the other, after the other, after the other. Now, 2 amino acids attached to each other would be considered a dipeptide. Many amino acids attached to each other would be considered a polypeptide. And that's when you start to get this string of amino acids in the primary protein folding, but they start to curve around and curl around and form alpha helices or beta sheets. So generally speaking, when you're looking at one turn of an alpha helix, there's going to be 3.6, I think is the number, 3.6 amino acid residues per turn. And in a beta sheet, there will be 3 to 10 amino acid residues per line. As I said earlier, the hydrogen, that attraction between oxygen and hydrogen is responsible for the alpha helix and for the beta sheet that is part of the secondary interaction. Now, again, the R groups are completely separate from this, so I'm going to be drawing some R groups here just to show you kind of where the individual amino acid residues are, and to, really press home the point that the R group is not part of that hydrogen bond. The hydrogen bond exists between amino acid residues that are separate from the R groups. So it'll be a partially negative oxygen on the carboxyl group of 1 amino acid residue that'll be attracted to a partially positive hydrogen ion that's about 3 amino acids down the line. This is not, in fact, the only attraction that causes an alpha helix or a beta sheet. There are other molecular attractions and configurations that are responsible for those shapes. However, this is the main one. Now, when we get to the tertiary level of protein folding, we actually do have to start addressing those R groups, because it turns out the R group attraction between R groups is the most important bond at the tertiary level. In order to do this, we have to take a closer look at those R groups. Now, there are 20 different amino acids, and what makes them different is the R group or the variable group. There's always an amine end, there's always a carboxyl end, there's always a central carbon. But the variable side chains make them different. Now, I'm not going to have you memorize the configuration of all 20 amino acids. However, I am going to ask you to understand that there are categories. There's 2 basic categories. The first we're going to look at is the nonpolar or hydrophobic category. What we understand about nonpolar structures is that they are not different from one end to the other. In other words, there is not like a partially negative and a partially positive end. The electrons are distributed equally amongst them. Now, nonpolar entities don't do well in polar structures. And for now, we're going to just kind of cover the idea that polar structures include solvents such as the fluids of your body. Water-based fluids are always polar. Non-polar things don't like it. It's actually right in the word hydrophobic. Hydrophobic means water-fearing or water-repelling, and therefore hydrophobic things tend to stick to other hydrophobic things, and they don't tend to find comfort in things like water-based substances. There's actually a good number of nonpolar hydrophobic side chains, and alanine is one example of this. A really good way. There's a few different ways to recognize hydrophobic structures, but generally speaking, they're going to be carbons surrounded by hydrogens. As you see here, alanine is the simplest of the hydrophobic side chains, in that it has just a CH3, C with 3 H's surrounding it equally. Now, the next category is going to be polar or hydrophilic. And as the name hydrophilic suggests, this means water-loving or water-attracted. And polar basically means this different from one side to the other, or different from one end to the other. And usually this means that there's going to be a partially negative part and then a partially positive part. The example we're showing here is serine. Here again we have our carbon with 2 hydrogens, but instead of that 3rd hydrogen, we have an OH group. And so we have this difference. Remember that I said oxygen tends to take on that partially negative, and then hydrogens are partially positive. So we're not sharing electrons equally. Instead, we are distributing them slightly differently. We have this partial charge, this partial negativity, this partial positivity. That's what makes this substance polar. Now, polar things like being present in other polar things such as water. To reiterate, non-polar amino acids such as alanine are going to be attracted to other non-polar amino acids. Polar amino acids will either be happy being exposed to the fluids of the body, or they will be attracted to other polar amino acids. I do have to take a moment and talk about one special amino acid, which is cysteine. Technically, cysteine is a polar or a hydrophilic amino acid, but it is so special that it actually deserves its own little category here. So cysteine's configuration, again, we're going to draw that central carbon so you understand where it's attached to. And then we're going to draw, guess what? A C with two H's. And then at the bottom, we're going to go ahead and draw an SH. There is going to be a sulfur attached to this one. So this is what we call a sulfide group. It's an SH is a sulfide group. And it turns out that sulfides are specifically attached to other sulfides. It's so special that we actually look for these cysteines or these sulfurs or these sulfide groups because they're so special. They actually cause huge differences in how a protein will behave. And so when we want to kind of investigate what a protein is doing, we actually look for cysteines specifically. Cysteines tend to be attracted to other cysteines. They form disulfide bonds, or it's also called a cysteine-cysteine bond, or it's called a disulfide bridge. One amino acid, so special, cysteine. Now, if we go back to that tertiary structure, remember that the R group attractions actually allow for that tertiary structure to take place, where you take an alpha helix and then you take a beta sheet and you kind of put them together in different ways. They fold together in unique ways, and this is the purview of the R group. So let us say that we had one area where there were a large number of hydrophobic R groups, and there was another area where there's a large number of hydrophilic R groups. And then we had a couple of areas where we actually spotted a couple of cysteines. We'd be able to predict that, this cysteine is probably attracted to this cysteine over here. And so we'd be able to actually predict the way that this is folded together. We've gotten extremely good now at predicting exactly how a protein folds together, which you think, well, that's not a very interesting way of doing research, but it's actually incredibly important because the way that a protein takes shape has everything to do with its function. The shape of a protein denotes its function. The shape of a protein denotes its function. The protein is allowed to have a particular physiological function because of the way it is shaped. And so when we look at the secondary bonds and all those hydrogen bonds and kind of the predictability of the alpha helix and the beta sheet, and then when we look at the tertiary structure and we look at how we can kind of predict based on how many amino acids in a row are hydrophilic or how many are hydrophobic, for example, we can start to predict certain things about, well, maybe this part of the protein is embedded in a membrane, or this part of the protein allows for an opening where something can attach to this particular protein. And so this tertiary function, these R groups, and even going back to the secondary function, allows us to have particular shapes, and that allows our proteins to have particular functions. Now, technically, the tertiary level only allows us to create a subunit. It's possible that separate subunits can be attached to each other to form this quaternary structure, which is where you'll have several separate, technically separate proteins attached to each other to make a larger protein. When you have a larger protein made of several subunits, those smaller proteins are no longer called proteins, they're called subunits, or they're called polypeptides. The most famous among these, the most well-known protein probably that we have, the one that people actually oftentimes know what it is and what it does, is hemoglobin. Hemoglobin is actually made of 4 different subunits, and you can actually see, now that you look at it, you can actually see where, I think I might be able to see where an alpha helix or a beta sheet might be amongst all these different subunits. So there's 4 subunits, 4 polypeptides, which means multiple peptide bonds, of course. And now we know that the peptide bonds exist between amino acid residues. And so 4 different subunits attach to each other to make a much larger protein. That's the quaternary structure. So each of the subunits has a tertiary structure, and then together all 4 of them have a quaternary structure, and that allows for the full functionality of hemoglobin, which is the primary oxygen carrier in our blood and responsible for the red coloration of our blood.